Hi everyone, my name is Mohammed Khaja and I will be talking about client-side machine learning with Tensorflow.js. Artificial intelligence is a field which seeks to build algorithms that automate tasks which require some form of intelligence, such as recognizing spoken speech, faces, objects in photos, playing games, translating text from one language to another, and so on. Machine learning is a subfield of AI and it deals with algorithms that learn from data. There are three kinds of machine learning. The first and most common is supervised machine learning, in which the data takes the form of inputs and outputs, and the task is to predict the output given the input. So you give the model a picture of a cat and it tells you that it is a cat. There is unsupervised machine learning, in which there are inputs but without outputs, and the task is to find clusters or patterns in these inputs. So you give the model a bunch of unlabeled gray points and it would find groupings that make sense. Reinforcement learning, there is no explicit input-output given to the model, and the task is to learn a model of the environment and how to optimally act on it. In this lecture, I will be focusing on supervised machine learning with neural networks. This is a dataset of horsepower versus kilometers per liter for various cars. Every data point on this graph is a car. As the kilometers per liter increases, so does the efficiency, because the car extracts more kilometers from every liter of fuel. Suppose we are designing a car with a horsepower of 175, and we would like to figure out what is the expected kilometers per liter for that car. To answer that question, we would need a box that takes as input the horsepower and outputs a kpl. As an initial attempt, we could use a line box or a line function. This function would take the horsepower, multiplies it by beta 1, and adds a bit of a coefficient beta 0 to give you the kpl. So you could have a line that looks like this, or a line that looks like this, or a line that looks like this. Obviously, there are infinitely possible lines depending on the value of beta 0 and beta 1. So which line should we choose? To answer that question, we need an objective function. One sensible metric is the average of the differences between the observations and the line. So in this example, I'm showing with purple lines the difference between 4 observations and the line. If we square those differences and average them, we get a familiar or common objective function known as the mean squared error, which has nice mathematical properties and turns negative differences into positive ones because we don't really care whether the line is above or below the observation, we just care that it is close enough. Using this objective function, we can apply brute force search, which searches over possible pairs of beta 0 and beta 1, and picks the one with the smallest mean squared error. So we could pick 10 values of beta 0, 10 values of beta 1, which means we would examine 10 by 10 equals 100 possible combinations. Applying this procedure gives us this line, which has clearly a better fit than the previous line. However, there are problems in that the line appears to severely underestimate the kilometers per liter for high and low horsepower. And importantly, when the horsepower is greater than 250, the line says that kpl will be negative, which is physically impossible. So we probably want something that doesn't look like a line. We can solve some of these problems by applying an exponential function to the right-hand side of the linear equation. Exponentiating gets rid of negative kpls no matter how high the horsepower is, so we will never get a negative number as an output. By applying the brute force search strategy to this model, we get this best fitting curve. And if we measure its mean squared error, we can see that it improves on the linear model, as it has a mean squared error of 3.78, which is lower than the linear model's 4.38. So far, we have a model that consists of a single neuron. It takes 2 inputs, a constant input with value 1 that gets multiplied by beta 0, and the horsepower input which gets multiplied by beta 1. Adding these weighted quantities together gives us the input to the neuron. And then when we apply, for example, the exponential operator, this is known as the activation function of the neuron. We have seen so far a linear activation function and an exponential activation function. The beta 0 is special and is known as the bias of the neuron, and it serves as a way to establish the baseline level of activation of the neuron. Beta 0 and beta 1 are known as free parameters of the model because they are determined from data. Determining them from the data is known as training or fitting the model. Now let's expand this to a network of neurons. We break the direct connection from the input to the output and introduce 3 hidden neurons in between. Every hidden neuron also takes a weighted summation of its inputs and applies a tan H or hyperbolic tangent activation function. This is yet another function. It takes any number, negative or positive, and maps it into the range -1 to +1, as you can see on the bottom right. And then on the output neuron, we have the usual exponential activation function applied to the weighted summation of the hidden neurons' activations. This model has 10 free parameters because there are 10 connections in this diagram. If we were to examine 10 values for every one of these parameters, the brute force search would result in combinatorial explosion because you will have to explore 10 to the 10 possible configurations of parameters, which is clearly too much and not scalable. The solution to this is known as the backpropagation learning algorithm, and the intuition is simple. You start with random parameter values, then adjust the parameters in the direction that minimizes mean squared error. Suppose you have a model that has a single free parameter, and suppose that this is what its loss function looks like. So for every value of the free parameter, this is the mean squared error that you get. Backpropagation starts by starting at a random point, for example this one, and computing the gradient of the loss function with respect to the free parameters and taking a step in that direction. So you would take a step like this. And then you would repeat the procedure again and until you converge onto a minimum point. And that minimum point is your best solution. That's the best value of beta. In reality, you will not have such a nice function, as your function will most likely have multiple local minimums, like this one. So here we have a global minimum and we have a local minimum. And the one that you converge on depends on where you start. So if you start on the far left, you will converge on the global minimum, but if you start somewhere in the middle, you will most likely converge on the local minimum. And that's why people, for example, sometimes restart training multiple times and pick the best one. Let's fit the network to the cards dataset. On the right, we see the network initialized randomly. Red arrows indicate negative weights and blue arrows indicate positive weights. The thickness of the arrow indicates the magnitude of the weight. The bias terms here are all initialized to 0. Initially, the model achieves very poor mean squared error of 92.8. After 5 passes or epochs through the data, the model improves significantly and achieves an MSE of 32.36. After 10 epochs, yet another significant improvement to 7.8. And finally, after 250 epochs, the model achieves 3.63. And on the right, we see the final values and signs of the weights of the model. Okay, so I will be demoing a simple diagramming web application. The application recognizes 4 hand-drawn shapes, lines, triangles, rectangles, and circles, and it uses a neural network to recognize those shapes. Once a shape is recognized, the application will draw a nice vectorized version of the shape. So it would take the inputs and give you a vector version of them. We will only demo the recognition part of the app, which afterward it can easily be extended into a more useful diagramming application that allows you to drag and drop shapes, for example, and so on. Sort of like a simple Visio, Microsoft Visio. All of this action will happen in the web browser. Nothing will ever get sent to the web server. So now I will demonstrate the shape recognition flow overall. First, a user would draw a shape on an HTML5 canvas. This drawing will be downsampled and resized into a 30 by 30 pixel image. Then, this 30 by 30 image will be flattened into a long 900 element vector. The vector consists of ones and zeros. When there is a 1, it means that the pixel is on, and when there is a 0, it means that the pixel is off, as indicated here by black and white squares. This input will be then given to a neural network that has 900 inputs, a hidden layer of 10H units, and a output layer with 4 outputs using softmax units. The softmax units ensure that the outputs all sum to 1. So we can interpret those outputs as what is the probability of a line, what is the probability of a triangle, a rectangle, and a circle. So the softmax always ensures these sum to 1. Afterwards, we would select the prediction that has the highest probability. In this case, it is the probability that it is a rectangle. When we will train this neural network, we will be using a different objective function known as categorical cross entropy, which is the probability of the observations. It is important to note that when we do the downsample and resize operation, we do a little bit of normalization. For example, if the user draws a rectangle, an actual rectangle, the resize operation will put that into a 30 by 30 image without preserving the aspect ratio. So the image would still look like a square. And the reason is we really only want to know what shape it is. We don't really care about the aspect ratio. We can implement the aspect ratio by recovering the bounds that the user has drawn, as we will see in the app. So now to implement this model, there is something called Tensorflow.js. Tensorflow is a graph computational engine written in JavaScript, and it uses WebGL for accelerating math operations. It makes implementing neural networks really easy, as we will shortly see, and it calculates derivatives automatically without any math required. So here is the model that I just described in the previous slide. First, we define that we will be using a feed-forward neural network architecture, meaning that it has stacked layers, one layer after the other. This is the simplest, most common form of neural network. Then we will define the type of the hidden layer. The hidden layer has 900 inputs, it has 10 units, and the activation function is 10H, and we will be using the bias terms. Then we define the output layer, which has 4 units and also uses a softmax activation function. We then define what kind of backpropagation algorithm to use. There are many backpropagation algorithms out. They have different strengths and weaknesses, but usually a default choice is one called the Adam optimizer. And these algorithms basically help the learning process avoid getting stuck in local minimums or accelerate learning. This number, 0.001, is known as the learning rate, and it can be manipulated to achieve better or faster training depending on your data. And finally, we initialize the model by compiling it. We specify the optimizer, we specify the objective function, which is categorical cross entropy, and we define the metrics to report when the model is being trained. In this case, it's just accuracy, how many things it got right. To train the model, we provide it with a list of training inputs and outputs. The training inputs is a JavaScript array with 900 element subarrays. Each subarray contains the pixels that are on and off in the image. The training outputs is a JavaScript array with 4 element subarrays. Each subarray is a one-hot encoding of the label associated with the corresponding image. One-hot encoding turns one bit on and turns all other bits off. So a square would occupy the third bit, a circle would occupy the fourth bit, and so on. The method fit on the model class allows you to train the model. You provide it with the training inputs and outputs, but you have to convert them or wrap them into a TensorFlow tensor class. This class adds additional methods and properties that TensorFlow needs to work. The call to the fit method also allows you to specify the number of epochs to run, whether to shuffle the data or not, which is usually recommended, and any callbacks to call after finishing certain events, such as finishing epochs. Since the fit function or method is a long-running function, we have to add to it the await keyword. Await basically tells JavaScript to return from the function immediately and not block the UI thread. To infer or predict the shape of a user-drawn image, we put that shape in an array called testing inputs and pass it to the predict method of the model class, again wrapping it in the tensor class to allow TensorFlow to work with it. The result of this call will be a tensor, which is 1 row by 4 columns. 1 row is because there is only one testing input, and 4 columns is because we have 4 shapes to deal with. Every column contains the probability of the shape. Like in this case, it's 30% estimated to be a line, 10% triangle, 50% square, and so on. We convert that into a hard decision by taking the argmax along the columns of the matrix. So argmax gives you the index of the maximum element along a certain dimension of the matrix. In this case, we get it along the columns. So it would give you the number 2 because number 2 has the value of 0.5, which is the highest in the column of the matrix. Then we convert the result into a regular JavaScript array with the array sync method, and that allows us to process it in the rest of our code. The result of this will be a regular JavaScript array with a single element 2, which is the index of the square label. This web application demonstrates the concepts in this lecture. On the left-hand side, we see the training set that can be used to train a model to recognize shapes. If we scroll down, we can see examples in this training set. Every example has the image, the associated label, and the model's prediction. Initially, the model is using random weights, so its predictions are random. To train the model on the training set, we click the Train Model button at the top. Once the model is trained, the predictions are updated, and we can see if we compare a few examples that is performing fairly well on all the examples, getting everything correctly. Now we could test the model on the right-hand side by drawing new shapes and asking it to predict them. So it correctly predicts a triangle, rectangle, line, and an ellipse. Now we can also add new examples to the training set by going to the left-hand side and drawing the example. For example, I'm drawing a square and selecting the associated label. In this case, it's a rectangle because rectangles include squares. And we then click Add Example. And we could do a triangle, for instance, and so on. Now we could retrain the model to incorporate the new shapes. One thing to notice is that our application is capable of preserving the aspect ratio of the drawn shapes. If you recall, the neural network does not actually give any information about the aspect ratio of the shape. Like from its perspective, this shape is a rectangle, but so is this one. clearly the two have very different aspect ratios. And the reason we can do this is because we have enough information to get this aspect ratio correctly, because we know the extent of the drawing and where the user started and stopped drawing. So this is an example of us complementing the neural network with a bit of expert knowledge to make the entire pipeline better without using too many examples. So where to go from here? One thing is to validate the model quantitatively by measuring its accuracy on unseen examples. These are examples that the model hasn't been trained on. This would give you an indication of how well it would do when the user gives it a new shape and asks it to predict it. Another is to train the model offline on a powerful machine, say using the Tensorflow library in Python, and then deploy it to the client. This way the user doesn't have to retrain the model every time they load the page. And of course we can use convolutional neural networks, which are special neural network architectures designed to handle images, exploiting things such as local proximity and parameter sharing. And the good news is that all of these things can be done and are supported by Tensorflow.js. And thank you.